Yes. 18.4, complex DC circuits. Today we're going to learn how to solve these complex DC circuits, and we'll describe a couple devices that we use to make circuits a little safer. So, first of all, safety with circuits. Short circuiting. This is what happens when you have a low resistance and a really high current, and it causes the wire to melt. And when it melts, it can catch things on fire. So try not to have short circuits. This can happen in your house if you have too many appliances, especially in the kitchen, plugged in. So like on mine, if I run the toaster and the microwave, which are on the same outlet at the same time, it trips the outlet and causes it to go off. So if the outlet didn't turn off, then it would short circuit and start a fire. Or it could start a fire. It doesn't get done, but it could. All right, a fuse is a very short piece of metal that melts before the current gets too high. So it's usually made of a different piece of metal than the rest of the circuit. And you've seen fuses in your car or in those light bulb strands that you put on your house for Christmas. They're just like these little tiny, very delicate wires inside a little, like they got metal on the other sides. And it just completes the circuit when you put that in there. And this will melt before the rest of it. So instead of causing the whole thing to catch on fire, the thing will melt and break the circuit, and then electricity won't flow. So you have to go and replace those fuses. And fuses are pretty cheap because all they are like wire that's not as strong as the rest of it. It can hold a less current than the rest of your circuit. A circuit breaker is a little bit more expensive. It's a switch that opens the circuit when the current gets too high. I'm sure you've heard of your parents going in and flipping the breaker, or they send you down in the dark when you have the vacuum and the microwave on and the dishwasher and it's all running, and then all of a sudden your whole house goes dark, or at least one room goes dark. It's like,
let me go down. Where do we go down to? We live in Florida.
Okay, well, normal people would go down to the basement. Here, I guess you guys go to the garage.
That's in my hallway.
In the hallway.
Weird.
Where's your breaker? That's what to do.
Ours is in the garage.
Oh, okay.
So how's the 2-hour trip from Georgia every day?
But yeah, I mean, I'm from Oregon, so it's always usually in the basement. I guess in one of my houses it's in the garage, but anyways, circuit breaker. It gets too high a current and notices it, and it switches off. So it breaks the circuit. So it'll turn everything off. You can turn your microwave off, turn your oven off, and then when you turn it back on, those things are off so that the high current is already flowing. If you had everything plugged in and it didn't turn off when the circuit breaker turned off, and you turn it back on, the breaker's just going to flip again. So you got to make sure you turn those things off so that the high current isn't going through. Because again, this is to prevent fires, right? I was going to say forest fires, right?
Only you.
House fires. All right, so that's the basic safety that you need to know about these circuits. The stuff that we'll be playing with in here later is not a big deal. You can touch it. The worst you're going to get is a burn on your finger. So be careful, but it's not going to start fires for you. All right, so now let's talk about combination circuits. This is a combination circuit. You can see here we have a light bulb. It's in series with this ammeter, and it's in parallel with this voltmeter. So we're going to talk about things that are both in series and parallel. They're like nested circuits inside of each other, and they turn into these really big puzzles that you have to solve. So what is, just like that grid, we're going to do the grid again. What is the potential, resistance, and current in each one of these? All right, here's some more. This is a nice basic one we have. This one's in series with these two that are in parallel. So if we wanted to break it down, you want to simplify the circuit. The best way to do this is to work for the resistor that is the furthest away from the battery. For our combination circuits, we're going to stick with one battery. So it's kind of easy to determine which way you need to solve. If it has more than one battery, it's going to be Kirchhoff's laws. If it only has one battery and it's all these nested things in it, then it's going to be your complex circuits. All right, so you can see these two are in parallel, and we know that in parallel, 1 over R plus 1 over R is going to equal our 1 over our total resistance. So we can find the resistance. We can just kind of smash these two together and find the equivalent resistance. So once we smash these two together, it becomes the resistor BC. So this is resistor B, and that one's resistor C. So we'll just use our parallel stuff to make it nice and simple. And then we have two resistors in series. We can add them up, because in series you just add up resistance, and you end up with a nice, easy circuit to solve.
Oh, that was so nice.
You couldn't do that?
That's why I taught you Kirchhoff's laws first, otherwise you try to solve them like this. Yep. All right, so this would be, this is our circuit, but then we can simplify it using different steps.
Quick question, when they do test, do they look at your work? What you write down?
The free response, they do.
Darn.
And you get points for what you write down. All right, so some circuits have series and parallel all together, and we're going to apply rules for parallel and series circuits separately. So you have to treat one little portion as a parallel and then another little portion as series. You might have to keep doing that until you simplify it into a nice, easy-to-solve circuit. So this one we'll solve for parallel first until we pretend like it's one resistor, get the equivalent resistance for that. And then we can smash these two together and just make it a nice, easy series one. Now, it's not always like this. You'll see, they're not all easy like this. Here's another one. You can see here we have 3 in series. If we smash that down into 1, then we just have a nice parallel circuit. So let's try one. 'Cause I know this is what you want to do. Smashing them together.
There was one thing I thought I was going to do with my life, but maybe my head against the wall.
All right, we have and I don't have any numbers on this one yet. We're just going to look at how to solve them on this one. So which one, where would you start? What are you going to smash together first? Go ahead.
Those 3 on the right.
The 3 on the right. So these are in series with each other. So if we smash those down all to 1, we can redraw the circuit. All right, now what do we simplify? Somebody else? All right, go ahead.
Parallel circuit.
The parallel circuit, we're going to simplify that. We'll smash that together. And now it's going to look like this. And then we have a nice series circuit to work with. So we'll use series to combine that resistance. It'll look like this. And then we'll use parallel to combine those two. And then this resistor represents all this extra stuff. And then we can solve. What we usually do is solve for resistance. So 1, 2, 3. And then once you get this, you're going to know the voltage of the battery, and you'll find current. And then using the rules for current and parallel, what's constant and what's not, you solve it all the way back. And we'll go through one. Okay, so now we're going to try one with numbers. Can I erase this? All right, we have resistor, 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 resistor. This is 18, and I'm going to go 1, 3, 4, 2, 5. Vert. One, 2, 3, 4. 5, and total. This just keeps track of our numbers. We have an 18-volt battery. Resistor 1 is 220. Resistor 2 is 130. Resistor 3 is 470. Resistor 4 is 100. And resistor 5 is 270. Now remember, it's not a series circuit, it's not a parallel circuit, it's a combined circuit. So what do you want to combine first? Go ahead.
170?
Well, just tell me up here.
4 and 5.
4 and 5. And 4 and 5, are they in series or parallel?
Series.
Series. So I'm going to redraw this. Now, you do not have to redraw, but I do recommend redrawing it the first couple that you do until you get good at seeing them. So this would be 1, 2, 3, and 4, 5 smashed together. Then what? Go ahead.
3 and 4, 5 in parallel.
They're parallel. Good. So we're going to simplify this circuit once more. 1, 3, 4, 5, and 2. So this will be our progression. Now we're going to start with resistance, and then I'm going to show you how to work your way back. So looking at, we'll call this A, B, and C. Going from A to B, we have to smash together 4 and 5. They're in series. So resistance 4, 5 is going to be, because they're in series, resistance 4 plus resistance 5. So R4, 5 will be equal to 100 plus 270. Now the next step from B to C, we're going to go 3, 4, 5. 3 and 4, 5 are parallel with each other, so 1 over R3, 4, 5 is equal to 1 over R3 plus 1 over R4, 5. Now they're 1 overs because they're parallel with each other. Please let me know if you get stuck on anything, because you have to ask questions while I'm doing it, otherwise it's really hard to answer your question. Okay, so I'm going to plug in the numbers for this. 1 over R3, 4, 5 is going to be equal to 1 over R3, which is 470, plus 1 over R4, 5, which is 370. So R3, 4, 5 equals, let's do a little math here. 1 over 470 plus 1 over 370. 1 divided by our answer gives us 207. And now we have a nice, easy series circuit right here. So we're going to find R total. Since it's in series, you can add them up. R1 is 220. Plus R2, which is 130. Plus R345, which is 207. So R total is 557. And we can write that in this box over here. 557. I want to put it in the box here. Now we have the total resistance for the circuit. We have the voltage. And whenever you have two of these boxes, you just use VER to solve. So we can go V total equals I total, R total. V total is 18. I total is what we're looking for, and R is 557. And that gives us 0.032. Go. And we can put that in here. Okay, now comes the tricky part. This is where people get stuck. You have to start back here. Right, this is where we're at. So these are in series. In series, what's constant?
I.
I is constant. So the I total is going to be the I for 1, the I for 2, and the I for 3, 4, 5. Notice the 3, 4, 5 is smashed together. This is not I for 3, I for 4, and I for 5. It's I for 3, 4, 5 smashed together. Okay, so now that we know this, since these are constant, we can fill in a couple of our things. 0.032, 0.032, and can't do anything else. Now we've got to move here. We went from here, where I is constant, to here. This I is for 3, 4, 5. Since we know 3, 4, 5, we can use ver again. B 3, 4, 5 equals I 3, 4, 5, R 3, 4, 5. So V 3, 4, 5 is what we're going to look for. I 3, 4, 5 was 0.032, and R 3, 4, 5 we found earlier is 207. Gives me, I put in too many zeros. 6.6. So our voltage is 6.6 for this 3, 4, 5. So now we're looking at this guy right here. In parallel, what's constant? Voltage. So this 3, 4, 5 is going to be the voltage for 3 and the voltage for 4, 5. So see, you're always asking yourself what's constant. And then the one that you just solved for is usually what's constant. And we move into it. Okay, so we just solved for V3 at 6.6. All right, we know V45. Let me move to a different color here. V45 equals I45, R45. V45 was 6.6. I45 we don't know, but we do know R45, which is 370. So 6.6, this is multiplied by 6.6 divided by 370. It says 0.018. That gives me I45. We're looking at these two now. I45. In series, right, these 4 and 5 are in series. In series, what's constant?
I.
I is constant. And we just solved for I. So that means that since 4 and 5 are in series, this will be the I for 4 and the I for 5. So we'll put that in here. 0.018, 0.018. And you're done. The rest of this, you use V equals IR and P equals IV to solve for all the missing stuff. So let's go ahead and do that. So 0.032 times 220, 7.04. Times 130, 4.16. 6.6 divided by 470, 1.29. 8, 270, 4.86. Now, with your simple series and parallel circuits, it was easy to just pick, oh, it's parallel, let's just do 18 all the way across. And that means that I would add up to equal our I. With complex circuits, you can't do that because they're complex. So the only way to check to see if we're right is to do the power part, which is why I've included it. Your questions don't usually ask you for the power, but it's how you double check. This is a lot of work to get the question wrong. So let's do the power. It's P equals IV, so multiply the two rows to get the last one. So 7.04 times 0.032. 0.225, 4.16 times 0.023, 0.133. 6.6 times 1.29, 8.5. 1.8 times 0.018, 0.032, 4.86 times 0.018, 0.087, 18 times 0.032, 0.576. I've made a mistake somewhere.
Wait, what was it supposed to equal out to again?
These things should add up to equal the end number. And I've made a mistake. This one doesn't seem right.
No, I think that one's a lot smaller. 6.6 divided by 470. It's not, I think it's 0.014. Pretty sure.
Yeah, that wouldn't be 1.29.
6.6 divided by 370.
470.
470. Yeah, I got 0.014.
Oh, okay. I did it wrong. Okay, 470 by 6.6. No, 6.6 divided by 470. Yeah, okay.
0.014.
I'm telling you, that daylight savings, it's got to go. It's no good. Because then we would be off kilter. All right, now let's add all these things up and make sure they equal what they're supposed to. Now, because of significant figures and on the rounding that we do, it's not going to be exact. It'll be kind of close. Is it exact?
It's exact.
Yeah,
Okay.
exactly.
Well, don't be concerned if it's a little bit off. If it's really off, then that's probably a problem. But if it's just a little bit off, then you're fine. So I'm going to do this real quick. Not that I don't trust your math, just because. Yeah, I don't trust anybody. I just don't trust anybody. How's that?
Speaking of daylight saving time, it's nice to know that every single school day is just going to get longer and longer.
All right. So this is correct. We have double checked. We did all that work, and it comes out. And obviously, you can kind of go through and be like, these make sense. When I had that, 1.29, it didn't look right. How do you feel about this? It's a puzzle. It's a puzzle. It's a process. If you get stuck, work through it. Remember, you can go on YouTube and look at this again. There's tons and tons of lessons on YouTube showing you how to do complex circuits. So if you get stuck, go and get unstuck. Because if you don't get unstuck, you're never going to learn it. It's okay to get stuck as long as you keep trying. Okay, question 1. Here's your first clicker question today.
Is this really this is one problem?
Yeah. Mm-hmm.
Is this like a question we get?
You've only
on the
got 4
test?
problems on your homework.
Yeah, and it's just long. It's not hard.
Yeah, well, it's complicated.
Yeah. There's a lot of steps to it. But just
Right.
myself.
The math part is not that hard.
Yeah.
The trying to unsolve it is hard.
Resistor 4.
There it is. I haven't started the clicker thing. It's taking its time.
So, wait, what you did on the board, that's kind of like something we would get on our test.
Yes. This will be your test, or a portion of it.